Hey there, y'all. Today we're going to start Unit 2 on relations and functions. And so 2.1 is on functions and continuity. And you'll see off to the right here our order of the unit. Just one note, you'll see that 2.6 and 2.5 are swapped. That is intentional. The sections here will match the book, but I am switching 2.6 and 2.5 in the order that we'll do them in terms of our lessons. Do expect a quiz after every second unit, so after section 2, section 4, and then section 5 with the flip is where we'll do those quizzes as we go through this chapter. So the objectives of this first section on functions and continuity. You'll be able to determine whether functions are one-to-one and or on-to, and be able to determine whether functions are discrete or continuous. And this falls under our standard of FIF4 here on interpreting key features of a function that the models relationship between two quantities when given in graphical or tabular form. Sketch the graph of the function for verbal descriptions including key features, and these would include intercepts, intervals where the function is increasing, decreasing, or constant, being positive or negative, and any relative maximums and minimums, lines of symmetry, and end behavior and periodicity. We won't worry about periodicity in this unit because that deals with functions that are periodic, and so we're looking at functions that repeat over themselves, and that'll be more in pre-calculus, so we'll look at that. So let's talk about a couple definitions first that we need to know. So our first definition here of a one-to-one function. A one-to-one function is a function where each element of the domain pairs with exactly one unique element of the range. And so we'll use a mapping diagram to see what this looks like. And so let's say I've got 1, 2, and 3 here. And then I've got 4, 5, 6, and 7 in the y's. And so 1 pairs to 4, and 2 pairs to 5, and 3 pairs to 6. To be one-to-one, every element of the domain has to have only one unique element of the range. So this is good, right? Now, let me show you an example of one that would not be one-to-one. So an example of not one-to-one, so I have my x and I have my y, 1, 2, 3, 4, and 5, is I have my 1 go to 4, my 2 go to 4, and my 3 go to 5. And so this would not be one-to-one because I have two elements of the domain going to the same element of the range. And again, if you look at the definition, it is exactly one unique element for each element of the domain. They've got to be different. They can't go to the same y value. So let's look at the second definition, which is onto. So an onto function is a function where each element of the range corresponds to an element of the domain. And so the relationship's a little bit backwards here when we think about this. And so here's our x's and here's our y's. And remember that the dependency in a function is from the x to the y. But onto makes us think about that actually in the reverse. And so if I've got 1, 2, 3 here, and I've got 4, 5, and 6 here, then what we're looking at is that every element of my range pairs to something, right, in my domain. And if I don't have that, then we've got an issue. So like we see here, we've got the 1, 2, 3. But if I include 4 here, right, what that would then have to do is come here to the 6, right? Or it can go to any of them. It would still be a function, right? But now I've got two different domain pieces going to the same range piece, which means it would not be one-to-one, but it would be onto. Okay? And so now we're going to look at what it means to be both one-to-one and onto. And so to fit both definitions, again, we'll use our bubbles here, our x and our y. So if I've got my 1, my 2, and my 3, and my 4, my 5, and my 6, every x will have exactly one y value, and every y will be matched up with an x. And so we've got to have them both to be one-to-one and onto. Now, a lot of times when we talk about functions, most functions are onto automatically. There are some exceptions when we think about the range of some of these functions. But when we talk about being one-to-one and onto, most of the time, especially what we're dealing with in Algebra 2, is going to be either at least onto or both one-to-one and onto. Okay, so let's look at some examples of how this affects us with our graphs. So in example 1 here, we've got a graph that is given with 5 points graphed, and we want to state the domain and range of the relation, and then determine whether the relation is a function, and if it's a function, we want to determine if it's one-to-one, onto, or both, or if it's neither one-to-one or onto. So let's go through this in the order given. So first we need to state the domain and the range of what we see. And remember, the domain, go back to Algebra 1, is the x values of all the points. And so if I look at my ordered pairs, I've got -4, -2. I've got 0, -2. -3, 1. This purple one here is at 1, 2. And this last one here is at 3, 3. So I'm going to list all of my x values. And typically we want to list those in numerical order from least to greatest. And so I would have the -4, the -3, the 0, the 1, and the +3. And we'll do the same for the range. And again, we'll list them from least to greatest. And in domain and range, you never repeat values. So if a value happens 2 times or 3 times or 5 times, then we're just going to write it once in our domain or range. And so I've got a pair that are at -2, so I'll write the -2. Then I've got +1, +2, and +3. So is this relation a function? And we're going to talk about ways to determine it in the end. But remember that for a function, I have to have that every x has a y, right? And so in this case, and remember that the y can only be one y, right? So we'll talk about the vertical line test in a minute. But do I see any 2 points that are vertical with each other? No. So this is a function. So yes, it is a function. And then, is this one-to-one, onto, both, or neither? And so the best way to determine this is to look at the mappings. And let me straighten this out a little bit. So we have our x, and we have our y. And so again, we'll list our values of our domain in the x bubble in order, and we'll do the same for our y's. And then we will draw the arrows across. And so the -4 pairs with the -2. The -3 pairs with the 1. The 0 pairs with the -2. The 1 pairs with the 2. And the 3 pairs with the 3. And so think about the definitions of one-to-one and onto. So let's start with it being onto. Does every y have an x? Yes. So this is onto for sure. Okay. The question then becomes, is it one-to-one? Does every x have a unique y? So the easiest way to think about this is, do I have 2 different x values that go to the same y value? And if that's the case, it's not one-to-one. And so in this case, we see that -4 goes to -2 and 0 goes to -2. So this will not be one-to-one. And so this function is only onto. So one thing I want to add back in is coming back up to this definition of one-to-one and onto. And the definition is that each element of the domain is paired to exactly one element of the range. And each element of the range corresponds to a unique element of the domain. It combines those 2 definitions, and I just want to make sure that is there. And so as we move on, let's look at the next example. So let's talk about the horizontal and vertical line test. We're going to start with the vertical line test first, which you should have seen in either 8th grade or in Algebra 1 talking about functions. And remember, this says that if I can take a vertical line across the graph and it never touches more than 1 point at the same time, then the graph is a function. And the converse is true as well. If any vertical line comes through and touches 2 or more points at the same time, then the graph is not a function. But the horizontal line test gives us a little bit more of information. And the horizontal line test says if there's no horizontal line that intersects the function in more than 1 point, then the graph represents a one-to-one function. So again, if I can take a horizontal line up the graph all the way up and down and never touch more than 2 points on the same horizontal line, then it is one-to-one. Now, that'll be important when we talk about inverse functions, and that we'll look at a little bit in Chapter 3, but you'll look more at in pre-calculus. But let's go ahead and look at example 2. So example 2, we want to graph this relation, determine the domain and range, and determine whether the equation is a function, and if it's a function, if it's one-to-one, onto, both, or neither. And then we also want to talk about discrete or continuous. Those are a couple terms we're going to define here in a second, and we'll determine that with this graph. And so first we want to graph y equals 2x minus 3. This is in slope-intercept form. Your slope is what? 2, because that's in front of the x here. And the y-intercept is what? -3. And so we go to -3 as our y-intercept. And our slope will take us up to and right 1. And we'll continue that line up and right as we go. And so taking that all the way up we get there. And repeating it in the opposite direction, so down and left, we get all of this. Now we will graph this line. And so we will graph it all the way through. Now, there are some lines that we won't do this for, but in general, if it just says graph the equation, we're going to graph it and draw the line and connect the dots. And so we want to talk about the domain and range. Well, the domain of this is the x values, right? And so what x values can this line be? And don't just stop with where the graph is. Like if the graph stops here, it doesn't stop at 7. The arrowheads mean the graph does what? It keeps going up. And the arrowhead this way means it keeps going down. But it also means it's going where? Left and right. And so that graph goes on forever to the left, forever to the right. And so that means that this is all real numbers for our domain. And another way we express that is what we call interval notation. And we're going to talk about interval notation as we go through this unit. And so it's going to go from -infinity to +infinity. And we'll talk about, why there's parentheses and some will have brackets, and we'll get into those details as we go along. But understand that this is going to go from -infinity on x all the way to +infinity. And remember that means that it goes on forever in both directions. When we look at our range, remember range is talking about the y values. What does it do for y? It keeps going up forever, and it keeps going down forever. And so what's that going to do? Again, we have all real numbers for the range, and we would do that in interval notation as -infinity to +infinity. So, next question is this a function? Well, does every x have a y, right? And not have more than one y? Yes, because it's a line, right? So if this were a vertical line, then it's not a function, or if this were like a circle on the graph, it would not be a function. But just a regular old line on the graph is a function, so yes, it is a function. Yes, it is a function. And so since we said yes to that, is this one-to-one onto both or neither? So remember, onto every y has an x. Does every y value have an x? Yes. Check. It's onto. The next question is it one-to-one? Yes. And so it is 1 to 1. And so it is both of those in this case because it passes the horizontal line test for being 1-to-1, and every y has an x, meaning it is onto. Okay. Last question is discrete or continuous. And so before we answer that, let's talk about the definitions of those two words. So if you scroll down in your notes just a little bit down to below example 4, you'll see these two definitions here. A discrete function is a function that has breaks in the domain. And so typically what you're going to see when we talk about a function that looks like that, it's going to be a collection of points. So it's going to look like this. And it could be some type of graph that goes up and down, or it could be points that are just along a straight line, but they're not connected. A continuous function is a function that has no breaks or gaps in the domain. And so it is going to be one continuous piece. Now, that piece may have an endpoint on both sides, or it may go on forever, but the key is that in between, in the middle of our domain, there's no breaks in between it. And so that's what we mean when we talk about discrete and continuous. And so let's go back up to example 2 and talk about that function. So look what we have drawn here. We have a solid line that continues on forever. Our domain is all real numbers, so there's no breaks in between there. And so this is going to be a continuous function. Now, continuous and discrete don't have to be for functions necessarily all the time either. So let's continue on as we look at example 3. So in example 3, we're going to look at how to evaluate a function. And remember that f of x is equal to x cubed minus 3 here. And we're going to find the value. And remember in function notation that this number inside here means that we're plugging that in everywhere we see the variable. And so in this case, we're going to plug in -2 everywhere I see x. And so that's going to give me -2 to the third minus 3. And -2 to the third is -8. And minus 3, so that gives me -11. So f of -2 is equal to -11. And this is one of the common mistakes with functions, and I want to try and make sure you're cleared up on this. This does not have anything to do with having to move across the other side and try and put it into the problem. What this value represents is the value that I have plugged in. It is the input value. And again, it could be a number, or as we see in example B, it could be a value that has another variable in it. And so let's look at how we do that with this. And so before we go to B though, how can I rewrite this answer of f of negative 2 is equal to negative 11? This represents an ordered pair. If this is the x, then that means that this is the y. And so I could rewrite this as negative 2, negative 11. Now we can do the same for b. We can look at our function here. And so everywhere I see x, I'm going to replace it with 2t. And so there's an x, so I replace it with 2t. I'm going to take that to the third power, and then I'm going to subtract 3. And so in this case, I've got to cube 2t. And so when we do that, we are going to distribute the cube to both. And so 2 cubed is 8, and the t will just have the cube on it, minus the 3. And is there anything else that I could do to simplify this problem? No, there's no like term. So this is the final answer, that f of 2t is equal to 8t cubed minus 3. Now, could I write this as an ordered pair? Sure. And then we could actually plug in a t value if we had a value to plug in for it and find the input and the output to it. And that would still work the same way in the end of that problem. Let's go ahead and look now at example 4. So as we look at example 4, we want to talk about how we understand if something is going to be a discrete or a continuous function when we graph it. And so here in example 4, we're given a table that shows the average fuel efficiency in miles per gallon for SUVs for several years. And graph this information and determine whether it represents a function. And is this relation discrete or continuous? And so when we graph this up, we'll have our years as the x. So it goes from 2001 to 2007. So 1, 2, 3, 4, 5, 6, 7. So this is 2001 and this is 2007 at this end. And you see where fuel efficiency is between 20, the lowest is 20.6 and the highest is 22.6. And so now we have a little way to kind of break this up. And you'll see this symbol sometimes if we're going to jump our graph so we can highlight and focus on data in a particular area. And so I'm going to go to 20, 21, 22, and 23 because I want to see these decimal values. I want to see what the change is between each. Now, whenever you see that figure, understand that it's going to cause you to lose perspective of height. And so remember that, you know, the height of 20 is significantly less than the height of 21, even though if I really did the graph up to it, it'd be about the same, right? 20 and 21 would be here, and I've got 20 spaces below, right? So let's plot these up. So 20.8 in 2001, 20.6 in 2002, 20.8 in 2003, 20.9 in 2004, 21.6 in 2005, 22.3 in 2006, and 22.6 in 2007. Now, the question becomes, should I connect these points or not? These are individual data points. This is what happened in this year, right? There's no reason to connect these. And so in the end, this graph needs to be discrete because the information is discrete. We're not going to connect these points. Okay? And so let's look at the last example here, example 5. And choosing a correct model based on understanding if it's going to be discrete or continuous. And so a metro train ticket costs $5.25. The cost of taking the train x times can be described by the function y equals 5.25x, where y is the total cost in dollars. And we want to determine whether the function is correctly modeled by a discrete or continuous function. And explain your reasoning. So again, this one's not even actually asking us to graph it. But understand that if I were to graph it, what would it look like? Well, if I don't go anywhere, right, and we can talk about a table here for a second. If I take 0 trips, right, how much would I pay? $0, right, because I didn't go on a trip. If I take 1 trip, I paid $5.25. If I take 2 trips, that's now double, so I'm at $10.50. And this pattern would continue, right? So I'd be here, and then I'd have 1 and $5.25, and then 2 and $10.50. So that's here, right? But would I connect the dots? Now, back in Algebra 1, we always connect the dots, and we just dealt with it, right? But can I take half a trip on this train? If I get on the train, it's considered a trip. So it's not like I take half a trip and I pay half the price. I get on the train, I pay $5.25. So these points are not going to be connected, meaning it is discrete because the fractional parts, especially with our domain, our fractional parts do not make sense to the problem. And so that's the explanation there. Again, the fractional portions, half a trip, a third of a trip, doesn't make sense to this problem. And so that's it for section 1. I hope you have found this good. Don't forget your Google form to fill that out, and I will catch y'all next time.